Hey, this is Horner, and this is Electricity Worksheet 4, and this is the solutions for number 1 as well as number 2. So what we're going to do is we're going to take a look at this one. Consider the combination circuit at the right. So why is it a combination circuit? Because it does have one resistor in series, and it also has two resistors, and those resistors are in parallel. Let's go through and do the paths so you can see how these work. We start here. We move across the battery pack. We go down to B. We're going to go over to E, and then we're going to go back up and across. So notice that that is one loop. Remember, the voltage in that loop should equal 0 when we are done. And then what we'll do is we'll change colors, and let's do, I don't know, let's do light blue. We're going to start over on this side again, and this time instead of turning right, we're going to go there and then turn right, and then turn right again, and then go all the way over, up and across, and there is our second loop. So the two resistors that are in parallel would be the 6 and the 12. So these two are in parallel, and then this one is in series. So that's the important part for these, and that's what we need to know in terms of where things are in the circuit. Remember, one of the things that I would do right off the bat is go ahead and do that private beach. So the private beach in South Carolina, because we know in parallel the voltage is the same, and in series the current is the same. So that is super helpful, I think, if you do that. They want us first to find the resistance of the circuit. So to do that, we do have something in parallel. So remember, whenever we have resistors in parallel on the equation sheet, it says 1 over the resistance, or the equivalent resistance in parallel, is equal to 1 over the first resistor plus 1 over the second resistor. So we've got 1 over 12 plus 1 over 6. And so that one, when you do your math, you're going to end up with 3 over 12. But remember, we've got to flip that, and so your resistance in parallel then is going to be equal to 12 divided by 3, which is going to be 4 ohms. So that's just parallel. They want the equivalent resistance. In this case, is going to be the parallel and the series. So if you're using a VERP chart, you've already used one VERP chart. Now you're using the second VERP chart, and this is the one that's in series. So we're going to say that the total resistance in series, or the equivalent resistance of the circuit, is equal to our resistor, which is 8 ohms. So this is the resistor that is 8 ohms, plus that resistance of the parallel branch, which is this right here. So we're going to take 8 plus 4, and that gives us our total of 12 ohms for the entire circuit. So now we've found the equivalent resistance. They want to know what is the current passing through each resistor, and then they want to know what rule is used. So to find the current through each one of these resistors, we need to use Ohm's law. That's not the rule, but we are going to use Ohm's law. And so we know that I, for the 8 ohm resistor, so we're going to do the 8 ohm resistor, and that is going to be equal to the voltage in the 8 ohm resistor, and that's divided by the entire circuit, which is 12 ohms of resistance. So I think what I'll do is I'll go back. I'm just going to get rid of these, and let's go ahead, and on the bottom we're just going to put the total resistance, because remember, when we put these together, now the whole thing is a series circuit. So the current in the 8 ohm resistor is going to be equal to the voltage, which is going through it, which is going to be 6 volts, and we're going to divide that by 12 ohms. So we're going to divide that by 12 ohms, because that's the total. 6 divided by 12 is going to give me 0.5 amps. So I know in this circuit, I have going through this resistor and then going through the branch, I will have 1/2 of an amp. The voltage going through that 8 ohm resistor, we don't know what that is. We're going to find out here, is equal to I times R. So that is the resistance in the 8 ohm resistor. and that is equal to our current, which is 0.5 times, and then we're going to do 8 ohms, and that is equal to 4 volts. So I know for this 8 ohm resistor, we have negative 4 volts going through it. So we're dropping 4 volts. And we also know that we have 1/2 of an amp. For this part of the circuit, we know that we have 1/2 of an amp going through the whole thing. So the current in parallel is also 1/2 amp. So the rule that is used there, remember, is called the junction rule. And the junction rule just says that the current going in needs to equal the current going out. So if this is one thing, the current going in is 0.5, coming out is 0.5, going into this resistor is 0.5, coming out is 0.5. Now we need to look at these resistors individually. So now we're going to jump over and look at the two resistors and the loops that are kind of going through those. So to do that, let's go ahead and we need to say, well, what is the voltage that is going through these two resistors? So we're going to say that the voltage in parallel, so if you're using the verb chart, you'll do the same thing, is equal to the total voltage in the battery minus the voltage that is going through the 8 ohm resistor, and that's 4 volts. So 6 minus 4 is going to give us 2 volts. So we know that each of these resistors, now we're in the inside of the circle, is 2 volts here, and this one is also 2 volts. If I know the voltage for each one, I can very easily find the current, because we know that the current in the 12 ohm resistor should be equal to the voltage in the 12 ohm divided by the resistance in the 12 ohm. The voltage is 2. We're going to divide that by 12, and that gives us 0.167 amps. In the 6 ohm resistor, which is this one here, we're going to say that the voltage divided by the resistance is equal to 2 volts divided by 6 ohms, and that gives us 0.333 amps of current. So now we've done that. Whenever we do current, we use the junction rule. Whenever we want to find the voltage, the rule that we use, remember, is called the loop rule. So you've got to remember these two rules. They will ask you, you just have to name them, and that will work out really well. So what is the voltage across the 8 ohm? Well, we already said that it is -4. So the voltage in the 8 is equal to -4. And then the voltage in both of these, we're going to make these negative since their voltage drops. So the voltage in the 12 ohm and the voltage in the 6 ohm are both the same, and it's what's left, and that would be -2 volts. Finally, we can do the power in each resistor. So we're going to say the power then for our, let's go ahead and do the 8 ohm resistor first, is equal to the current in the 8 ohm times the voltage in the 8 ohm. And so we said that the voltage is 4. We said that the current is 0.5. So we're going to do 1/2 of 4. And that gives us 2 watts. And the next thing we need to do here is say, well, let's do the power in the 12. Power in the 12 is equal to 0.167 amps. So that's this times the voltage. And we said that that was 2. So this one is equal to 0.333 watts. And then finally, the power in the 6 ohm resistor in parallel is equal to 0.333 amps. And we're going to multiply that times the 2 volts. And we end up with 0.667 watts. So a couple of things that you can do. If we were listing the brightness of these bulbs, we would say that the brightness, so the brightness of the bulbs would be resistor 8, and that would be much greater than resistor 6, and that would be much greater than resistor 12. So you'll see that this one, they don't go in order of resistance, it's just the order of power, but we put down which of the resistors are there. The last thing that we can do with this diagram is let's put in where we would put meters. And so what we'll do is let's go ahead and do this in a different color. Let's change this color to dark green. And if I want to measure the voltage here, I would put in a voltmeter. And so there's a voltmeter for the 12 ohm. I also would need a voltmeter for this one, which is the 6 ohm resistor. And I would need a voltmeter for this one. So we'll put a voltmeter in for the 8 ohm. And so there we go. Ammeters always go after them. So after the battery, we could put in an ammeter right here. For this one, we could put an ammeter in right here. And then this one, we'll put an ammeter in right here. And then finally for this one, we'll put an ammeter right here. So ammeter, this will measure the entire circuit. So will this one, believe it or not. This one will measure everything going through the 12. This one will measure all the current going through the 6. And that is the end of this one. Let's go ahead and take a look at the next problem. This is number 2, and this one's a little different. It says, suppose that the switch in the circuit at the right is closed. What effect does this have on the change in potential from A to B? So let's take a look at this circuit. Notice that right now we have a parallel circuit. When the switch is open, this part of the circuit would not work. Even though there's something going to it, you have to have a complete loop. And here I have a dead end, so it would not work. So if it was open like this is an open switch, we would only have voltage going through each one. So remember that whenever you have voltage, we want to use the loop rule. So this is why this works. In the loop rule, the voltage is always the same in each one. So right now, what we could do, here I'm going to switch pins again, is we could say that this has 6 volts going through it, and this one has 6 volts going through it. So if I close the switch, the thing that'll happen is this part of the circuit will actually work. So if I take this switch and I make the connection right here, now I have that last loop. So here is the last loop that's able to work. And as I go through, there's my last loop. I also will get 6 volts of push here. And so that one is 6 volts. So the delta V from A to B will not change. Okay, what effect does it have? So we would say there is no effect. And then we could say because the, and then you would say loop rule, states that in each loop, the change in potential should be equal to 0. And then you could say, therefore, A to B, C to D, and E to F all have 6 volts. And that's equal to the change in potential. For the next part, it says, what is the current in the first 2 resistors? So not what is the current, but what effect would it have in the current in the first 2 resistors? So notice that all 3 of these resistors are the same. And remember that V is equal to I times R. So the current is equal to the voltage divided by the resistance. So let's figure it out without this. We'll just do these 2. Well, 6 divided by 6 is going to give me 1 amp of current for this one. 6 divided by 6 will give me 1 amp of current for this one. And if I hook this one up, it will still give me 1 amp of current for this one. And these will not change because our current is going to be related to the voltage going through and the resistance of the resistor. So this one, again, no effect. And it's because all resistors are the same resistance. If the resistors were different resistances, that would change what's going on. So the last thing that happens is it wants to know what is the current through point G. So what's going to happen to the current through point G? So we've only talked about the current that is here, here, and here. So what I'd like to do is let's open this switch again. Okay, so we're going to just erase a few things. Let's get rid of this. And let's take a look at what happens with the current at G when the switch is open. So we're going to make a couple statements here. So if that switch is open, then we need to first find the total resistance in parallel, which is 1 over RP, and that's equal to 1 over 6 plus 1 over 6. So that would be equal to 2 over 6, but we have to flip both of them. So our resistance in parallel, if we just have the first two resistors, when that switch is open, is equal to 3 ohms. The current then at G is equal to the total voltage divided by the total resistance in parallel. And our total voltage we know is 6. Our total resistance in parallel here is 3, so that would be equal to 2 amps. That's if it's open. If it is closed, so let's go ahead and change to green. So now we're going to say if it is closed, then we're going to do 1 over RP is equal to 1 over, so now we're going to close this switch, which means that we have 6 volts going through this also. And this is 1 over the first resistor, which was 6, plus 1 over the second, which is 6, plus 1 over the third, which is 6. And that gives us 3 over 6. Oops, sorry. 3 over 6. And when I flip both sides, that means that the parallel resistance when it's closed is all 3 of them. So that is only 2 ohms. Because that's 2 ohms, our new current at G is equal to the total voltage divided by the total resistance. And so that is now equal to 6 volts divided by our total resistance, which is now only 2. And so 6 divided by 2 is 3 amps. So here, what happens to the current? It increases from 2 amps to 3 amps. And that is how we answer this question. This question is more along the lines of what you'll see on the AP test. The one before it is a skill that you really need to be able to do in order to do something like find brightness. But a real AP test will have a question that was going to be probably more like this, where some of the things you need to do some simple math, but you really need to understand the equations like you see here, and understand loop rule, and understand the junction rule. So those are the kinds of things that you need to know.